Good morning or afternoon or evening, depending where you are in which time zone. So welcome. Sorry, I changed the unintentionally. Okay. So welcome to the 38th IEEE International Conference on Computer Design that, as you know, was supposed to take place in Hartford, Connecticut, which is the home to a famous Connecticut Science Center and the birthplace of Mark Twain. So unfortunately, because of pandemic, we are missing all this great city and interesting events that we're planning for you. Hopefully next year we'll be in some real physical place for this conference. I'm Maciej Ciesielski, General Chair for the conference, and Resit Sendak is the Program Chair. I would like to recognize our sponsors, IEEE, and in particular, Circuits and Systems Society and the IEEE Computer Society. So the program, we have a rich technical program that is spanning 4 days. I will come back to that in a moment, but before I should start with recognizing the steering committee. So my first special thing is to the head of steering committee, Omar Khan, who actually guided us through the process and steered us in the right place and did a lot of fantastic work behind the scenes. We also have Kiput Sum Kim from Synopsys, Peter Michael Zeidel from University of Hawaii, Sandeep Kundu from University of Massachusetts Amherst, and Georgi Gaidadiev from Groningen, Netherlands. So we also have an organizing committee of a number of devoted people, and this is my special second special thank, a very personal one, to my former student, Jung-Chi Yu, who is not only a special session chairing the session that happened on Sunday, but also who helped us a lot with technical issues, including the one that we just had a few minutes ago with the technical difficulties, and who also helped me overcome the fear of doing this whole thing in virtual space. So thank you very much, Jung-Chi. So we had other devoted people that did that, help us with the conference, the registration chair, Daniel Halcomb, web shares, who put a lot of work on putting things on the web, Samah Syed and Masab Ahmad. We had proceeding chair, Fan Yao, and finance chair, Georgi Gaidadiev, and Rajesh Jaya Bharati. And also publicity chairs, Sebastian Piemont and Dominic Stoffel, who are responsible for sending information and emails to thousands of prospective participants in this conference. So as I said, the conference has a rich program spanning 4 days. We actually started yesterday on Sunday with 2 tutorials from Xilinx and then 3 special sessions that were run by, the whole day was actually run by Chung yesterday. Today we'll have the best paper session, in which we have 7 papers, and Resit will tell you a little bit more about this later. And we'll have a keynote by Vivian C from MIT. And this will be followed by the 2 parallel tracks, which between Monday, Tuesday, and Wednesday contain 18 regular sessions. And everything will be culminating with Best Paper Award session on Wednesday, at the very end of the conference. So yesterday we had 2 tutorials, one from Xilinx, one was developing high performance computing and machine learning accelerators using Xilinx FPGAs. And the second one was XTA, open source, extensible, scalable and adaptable tensor architectures for AI accelerations. All of those were recorded, and you can listen to them and watch these tutorials yourself if you go on our website, on the conference website. There were 3 special sessions yesterday, one devoted to quantum computing, the other one to adiabatic circuits, and then there was something about secure and trustworthy designs. The conference has 6 technical tracks. They are computer systems, electronic design automation, smart, autonomous, and embedded systems, logic and circuit design, processor architecture, and test verification and security. Our keynote speaker is Vivienne C. from MIT, and the talk will be about how to evaluate efficient deep neural network approaches. And with this, I will pass the floor to Resit Sendag, our program chair, who will tell you about the papers, the technical, more details about the technical program and the decisions, how the decisions were made in accepting the papers for presentations. So Sendag, it's...
Thank you, Maciek. So I would like to talk about a little bit on the paper review and decision process. We have 220 paper submissions to 6 tracks in total. So, and each of those papers were reviewed at least 4 or 5 program committee members. We had 203 PC members that covers 15 different countries with a healthy mix of academia and industry. So what happened was the PC members had online discussions after the reviews to reach consensus. And there was TPC meetings held by track chairs. This was online, everything was online basically. And after those TPC meetings, most papers were basically finalized, but we had some papers which were on the border. So we further discussed them by holding a final meeting led by me and the track chairs. So we accepted 63 regular papers and 24 short papers with an acceptance rate of 28%, 28.6% for the regular papers. And then after we made the decisions, each track committee selected the best paper of their track. Computer systems had 2 best papers selected. So we are going to see all 7 papers in the best paper session shortly. And we will have a best paper award. This will be selected by a special committee and will be announced on Wednesday at the conference closing. So these are the best papers. You will be seeing the presentations shortly, and you will have the chance to ask questions to the presenters. When we look at the submission by country, we have most submissions from US, 42%, followed by China, 25%, then India, 6%, followed by Germany, Taiwan, Japan, and so on. So I just wanted to share you these statistics. I would like to thank to track chairs who really worked hard to come up with this excellent program. Computer Systems Track Chair, David Calley from Northeastern University, Electronic Design Automation, Piran Kala from University of Utah. Smart Autonomous and Embedded Systems, Kunal Mankodia from URI and Hari Dubey from Microsoft. Logic and Circuits Design, Himanshu Taplial from University of Kentucky. Processor Architecture, Ala Mildin from Simon Fraser University. And finally, Test Verification and Security, Amro Awad from North Carolina State University. And finally, I would like to thank the session chairs. As you can see on the slide, I don't want to go through the names now. We don't have too much time. And I would like to thank all of you for joining the conference. Enjoy the conference. We will start with the best paper session. So I'll ask Maciek to let me share my screen. We can start. Okay, so let me see. Okay, so let me go to the program. Okay, we have 7 excellent papers. And the first one will be presented by John Lee. And I will play the recording. And during the recording, please, if you have any questions, just type your question on the chat window. So after the presentation, I'll ask the questions. So we have a tight schedule. So every presentation is for 10 minutes. Now we have 3 minutes for Q&A. So without further ado, we will start with the first presentation. Jung Jun Lee is a PhD student at University of California, Santa Barbara.
Hello, thank you for being here. My name is Jung Jun Lee, and I'm working with Dr. Peng Lee, who is my advisor. And I'm working at EC department in University of California, Santa Barbara. The topic of my presentation today is reconfigurable data flow optimization for spatial temporal spiking neural computation on systolic array accelerators. So I'll divide my presentation into 6 parts, and I'll first move on to the first part, the introduction of spiking neural networks. So the spiking neural networks, or SNNs, are motivated by biological neurons and synapses. So the inputs and outputs are represented with spikes across different time points. And if there is a spike from presynaptic neuron, it is multiplied with synaptic weight and integrated in postsynaptic neuron as membrane potential. If the membrane potential in postsynaptic neuron goes beyond a certain threshold, then the postsynaptic neuron generates a spike. So the SNNs are biologically plausible computing model, since it's mimicking biological neurons and synapses. And also it is well suited for processing complex spatial temporal data, and often used for neuromorphic processors with low power and event-driven processing, such as low EHE and true norms. With its many research interests, it is often called as third generation of artificial neural network models. However, if you think about the SCNNs or spiking CNNs, there are some challenges stemming from unique characteristics of SNNs. There are 2 reasons for this. So the first one is as briefly stated in the previous slide, the inputs and outputs are represented as spikes across multiple time points. So in conventional approach, it requires a time serial computations across different time points. So there is a complex spatial temporal interactions in data movement and computation. But despite this crucial impact, developing an efficient data flows for SCNNs has not been extensively studied. So this work proposed first a novel scheme for parallel acceleration of computation across multiple time points, and second, how the tiling strategy In particular, the positioning of the temporal dimension impacts overall performances. And last, a method for mapping feed-forward SCNNs on a sisterly array with optimized data flow regarding all the intertwined factors such as data reuse and storage stationary type or layer-dependent properties are proposed. So the computations in SNNs can be presented into 3 different steps. Step 1, spike input integration, and step 2, membrane potential accumulation, and step 3, spike generation. So in conventional approach, these 3 steps are performed in time sequential manner. So for example, at a given specific time point, these 3 steps are performed and we move on to the next time point. And again, these 3 steps are performed and so on and so forth. So these 3 steps are repeated over all the time points. But what we do is we perform a parallel processing across multiple time points for the step 1. So the step 1 is completely a dominant part of the total computation, but we do a parallel processing since we know all the spike inputs from the presynaptic layer. And step 2 and step 3 still remains as a sequential processing because we should know the final result of the previous time point to perform the step 2 and step 3. So if we think about this idea, we can represent those step 1, 2, 3 into equations, and we can map those equations onto the sister array. But this is not a trivial task because there are 2 factors that we should consider. The first one is the positioning of the temporal variable, and the second one is the data movement and storage. So if we think about a given number of time steps, the position of the temporal variable or the time dimension can make the accelerator better or even worse, so it requires a thorough study. And if we think about the data movement and storage, there exists a certain trade-offs between weight reuse versus memory needed for storing membrane potential. So there is a need for an optimized data flow for an efficient acceleration of SCNNs. So as for a specific example of data flow which exploits the temporal parallel processing, we'd like to show one specific data flow as shown in the figure on the bottom. So if you think about this data flow, in this data flow, all the partial sums generated in the sisterly array are pointing out one specific position in output feature map. And also the data processing associated with parameters of time steps and output channels, which are denoted as capital T and M, is parallelized simultaneously in a row-wise and column-wise manner. So if you think about the pros and cons of this data flow requires relatively small memory for storing p-sums, since the p-sums generated from the array are pointing out one specific position in OF map, but it requires a relatively large data transfer because of the frequent filter data transfers from different input channels, which is denoted as capital C. So it is obvious that there is a certain trade-offs for handling the filter and partial sum data, which are 2 main bottlenecks. For the SCNNs, input and output spikes, which are binary, is not a big concern. So for a large design space exploration, we built an SNN Dataflow Simulator regarding the unique characteristics of SNN. With given hardware resources and data flow and network topology, the simulator estimates overall performances, including runtime, energization, and etc. So with this simulator, we summarize 3 most promising data flows regarding the overall performance. With these 3 different promising data flows, we performed optimizations for given nets, the VGG16 and the AlexNet. So for the first, we performed an hardware optimization. So for a fair comparison, we've set an area constraint and explored the accelerator hardware optimization by allocating different area budgets for the compute units and on-chip memory buffer. So for example, less compute units will be matched with larger on-chip memory and vice versa. For the tiling strategy optimization or the data flow optimization, we demonstrated how the tiling strategy optimization works on a layer by layer basis for a given network. For two different networks, VGG16 and AlexNet, for two different area constraints, we checked that the jointly optimized tiling strategy and hardware leverages the EDP improvement compared to the conventional approaches that are based on the time sequential process. So if I summarize this work provides a knowledge base for developing an efficient SNN data flow, which has not been extensively studied. And also introduced a novel scheme to enable the parallel acceleration of computation across different time points. And we demonstrate how the tiling strategy can be reconfigured and jointly optimized considering all the intertwined vectors. Thank you for having me and thank you for listening. Thank you.
Thank you, Jeonjun. So now I would like to take questions. So we have time for 2 questions. Okay, so we have one question from Bing Wu. How do you manage the SLC blocks and MLC blocks in physical SSD device?
Hello. Can you hear me?
Yes.
Sorry. Can you please repeat the question?
How do you manage the SLC blocks? Not for, okay, so I guess
the SRC blocks.
This is not, sorry, I think
okay.
This was not a question for you, Bing Wu corrected me.
Okay.
So I would like to ask attendees if they have any questions. Let me ask you one question.
Okay.
So what are the pros and cons of the temporal parallel processing across time?
Yeah, okay. First, thank you for a great question. And I think there is a fundamental trade-off for exploiting the temporal parallel processing across the time domain. So if we do a parallel processing across time, the process that it enables the reuse of weight across different time points. But the cons is there is a need for storing the intermediate results or the partial sums or p-sums across the multiple time points. So I think there is a fundamental trade-off between the weight reuse and the p-sum storage.
Okay, thank you. So we have a question from our General Chair, Maciek. How are spike CNNs different from standard CNNs, standard NNs?
Yes, okay. So if we think about the standard neural networks, or I can say standard CNNs, the spiking CNNs are composed of the binary inputs and outputs. So it's basically exploring the spiking models into CNNs, which is considered to be a promising model because of its binary nature. Yeah.
Okay, thank you very much. So I'm gonna move to the next presentation. Our next presenter is Bing Wu from Huazhan Science or Technology in China.
Hello everyone, my name is Bing, a PhD student from Huazhong University of Science and Technology. It's my great honor to present our work DualFS. It's a file system about flash with dual mode switching feature. This is our layout. We will first give some introductions. Flash controller and flash arrays offer the significant performance improvement over HDD because of their inside parallelism. We can see from the overview of SSD, flash arrays are divided into multiple channels. chips, dies, plans to respond to every request by parallelism and pipelining. But some unpresent characteristics of Flash have to be dealt with carefully, such as the auto-place update property. That is, the read operation is at the block granularity, while the read and write is at the page granularity. So we need address mapping, garbage collection to management the flash memory. Certainly, flash manufacturers scale flash capacity by storing more bits in one cell. 1 bit per cell is called SLC, 2 bits per cell is MLC, 3 bits per cell, the TLC, and so on. But with the increase of more bits per cell, cell performance decreased. You can see from the table. The program latency is much longer in TLC or MLC than it's in SLC cell. Nowadays, a block has more pages. It causes the big block problem. On one hand, non-write latency makes writing 12 pages cost more time than an erase operation. On the other hand, the big block causes more pages migration during GC with a patently long delay. From the figure, with the increase of pages per block, in some benchmark, here the file server, a GC procedure may migrate more than 700 pages with a near 1 second delay. There is another problem with SSD. The file system and SSD work independently, which leads to semantic gaps. The host and the SSD device are both bluntly designed without knowing each other's schemes. As a result, both the host and the SSD manage their own address mapping, garbage collection, and the other redundant works. I will show that a data grouping scheme in FS that is broken by the device FTO algorithm. Data in the logical groups are mapped randomly in physical blocks. Open channel SSD and the dual mode switching of flash give a new chance for solving the above apparent OCSSD expose interface to the host so that FS and the device are no longer knowledge of each other. And the dual mode switching enable flash blocks to switch between the high performance SLC blocks and the large capacity MLC or TLC block. So we get a simple idea. With the help of OCSSD, we want to combine FS semantics to maximize the usage of SLC blocks to speed up the I/O requests. Now we come to our design. Here is the whole architecture. The FTO in our system is called LBLK. It only implements a segment mapping. All other management are achieved in FS. We first add SLC groups in FS, and then set the SLC admission rule with SLC Write Budget to utilize the SLC area. The GC for both the SLC and the MLC are united. The figure shows the structure of well-known F2FS file system. We have two main clusters, which are the node and the data. Both of them are further divided into 3 groups: hot, warm, and the cold. Each group has a corresponding active segment. So we just simply add 2 SLC groups to the data and the node clusters called the SLC data and the SLC node. Then we have to decide what kind of requests can be written to the SLC groups. We first use an equation to calculate the profit of one request based on its hotness and the priority. The priority levels of different kinds of requests are listed below, and the hotness is got directly by the classification of original F2FS. Only when the profit is larger than a threshold, the request has chance to be written into the SLC area. Next, the request that passed the first profit filtering will have secondary filtering. The general idea is that we only want to speed up critical requests, So we classify whether a request is critical by I/O queue deep first. The busier the device is, in other words, a queue is filled with more requests, we will give the more chance for the request to be written into the SLC groups. Moreover, the reader requests need to wait until the data is returned back from the device, while the write only has to submit a request. So if there are more read requests in the queue, the request has more chance to be written into the SLC groups. We also consider remaining capacity of SLC area. In conclusion, the secondary filtering is based on multiple dimensions, and we get SLC write ratio lambda. Data will be written into SLC area at ratio lambda in a given window. We noticed that writing SLC block will lead to more erase counts because the size of SLC block is half of the MLC block. The maximum size a device can be written is the maximum erase count times the capacity of SSD. We first set a goal for the device. The SSD need to support at least writing WMIN data. Our idea is to limit the data writing into the SLC groups in a certain data window. The remaining write size that needs to be guaranteed is WMIN subtract the data that are already written. So the data written to MLC area plus data written to SLC area need to be greater than W. The data written to MLC can be calculated by beta times X times M, where M is the MLC block size and the beta times X is the erase count that's consumed in the MLC area. Similarly is the data written to the SLC area. Finally, we solve the equation to get the maximum beta. So every writing delta size data, SLC write bucket is got by this equation. Let's review the whole process. If the SLC write bucket has been reached, the data will be written to the original groups. Otherwise, it will enter the SLC admission rule, and the SLC admission rule is judged by the profit filtering and how busy the device is. Last is the global GC. We implement a united segment mapping to align FS management size and device section size. There is only one GC procedure for both SLC and MLC area, and also for both FS and device. Finally, let's go through the evaluation. We use FIO as our test environment. FIO is a QEMU KVM-based virtual machine manager. Three kinds of benchmarks are used. They are FIO, FileBench, and Postmark. The comparison schemes are OCSSD-based FS AMF, and other dual-mode FTL. Here, DualFS no WB is a DualFS without write bucket, and the default write bucket of DualFS is set to 80%. All test parameters are listed. DualFS achieves higher throughput than all other schemes, and DualFS without write buckets gains more improvements. When it comes to random write and sequential write tests, UFS gains stable improvements as time goes on. Due to the speed up of critical requests, UFS also achieves lower read response time, and the right figure points out the dynamic adjustment about the SLC area. In this test, we changed the write bucket ratio from 80% to 95%. The writer bucket scheme works well as the lifetime meets the standards we set for it. This is also write bucket results for different FS in terms of erase count. We can see that straighter write bucket has fewer erase count. In conclusion, UFS successfully speed up the FS by dual mode switching with open channel SSD. Thanks for listening. This is all about it. If you have any.
Thank you, Ben. So I would like to open up for questions.
Yes.
Okay, so I guess we have one question over here from Julian Wei. How do you manage the SLC blocks in SSD device? Are SLC blocks fixed in the SSD device? He has many questions, I guess, but I'll just ask you the first question.
Questions.
Okay, if you can see the question, please go ahead.
Well, the SLC area in SSD are not fixed. In fact, we only add SLC node and SLC data header in the file system. Every time the SLC header allocates a new SLC block, we switch a physical block to SLC mode and do the address mapping. So every physical block can be SLC mode or MLC mode. Okay. The second question I see is how does the SSD lifetime evaluated? Well, we evaluate SLC lifetime by running each benchmarks, and then we capture the data size that's written to the SLC and to the MLC area. So we also can capture the erase count of each physical blocks. And by using this information, we are able to calculate the maximum size of data that can be written to SSD on the data pattern of the benchmark.
Okay, thank you. Let me ask you a question. How does the write budget scheme meet the standard you set?
Yeah, we use the equations. You can run the video. We use the equations. We determine the beta, which is the erase count allocated to the MLC area, and the last erase count is allocated for the SLC area. By calculate the data write to SLC and MLC, then plus them two, and we should the data should be greater than the the goal we set at first. In short, we set a goal for the minimum writing data, and then we calculate the data write to SLC plus data write to MLC. This should be greater than the goal.
Okay, thank you very much. So we will move to the next presentation. The presenter is Lake Bu. He is a senior engineer at the Charles Stark Draper Lab in Cambridge, Massachusetts. He received his PhD from Boston University in 2019. So the paper is about quantum crypto system. So let's start the presentation.
Hello everyone, this is Lake Bu from Draper Lab. And today I'm going to present the paper titled Quantum Proof Lightweight Mac-Lease Crypto System Co-Processor Design. And this work was done with my previous lab mate Rashmi and also my PhD advisor, Michael Kinsey. So this is the presentation flow. And firstly, we're going to talk about the motivation, which is why we picked the public key crypto system and why the classical public key crypto systems are not secure under quantum computers. And what can we do? So public key crypto systems are very useful. And with the public and a private key pair, we can do encryption and authentication in different ways. And it can be used for transmitting AES keys or do digital signatures or authentication on internet. And the most common algorithms we now use today are RSA and also ECC. And everyone is pretty happy with these two algorithms since they're considered as secure until one day we saw that the rise of quantum computers, and many companies from large to small are making quantum computers, and it's still growing. And one day we start to see from news media and reports with titles, scaring titles like this, like quantum computers can kill encryption. It looks like that when quantum computer comes, and the current encryption schemes will no longer be usable. And these titles can be scary, but what's actually happening is that there are quantum computer-based algorithms that can break the fundamental security assumption of classical crypto. So for example, the Shor's algorithm is a quantum algorithm that breaks this fundamental security assumption of RSA and ECC, which means as they're pretty secure on classical computers, for example, they can provide at least 112-bit of security level or 256-bit of security level. When quantum computers become feasible, and now they're only left to about 30-bit of security. And remember that a system should have at least 112 bits of security level in order to be called secure. So if the RSA and the ECC can only have about 30-bit of security, this means that they can be broken in a snap of finger. And what can we do with it? So NIST has launched a post-quantum crypto standardization campaign in 2017. Its goal is to find algorithms that can replace RSA and ECC that can resist the attacks from quantum computers. And so far it has come to the third round. And the two most likely winning algorithms are lattice or learning with error-based algorithm, and also Mackey-Lee's crypto system. And unlike the young learning with error algorithm, the Mackey-Lee's system is very old, but it withstands the test of time. So it's old, but definitely not obsolete. So the Mackey-Lee's crypto system, it was invented by Robert Mackey-Lee, and it's based on the error correction code that we saw every day. And it never gained much attention when it was invented until the quantum computers become a threat. This is because the security assumption of this Mackey-Lee's system is decoding linear codes can be hard. And the people have found that it is also hard for quantum computers. So the Mackey-Lee's crypto system can be explained in a nutshell in this way. So firstly, Alice creates a key pair, which is public key and private key. And it uses the error correction codes, generating matrix, and it transforms it with the singular matrix S and a permutation matrix P. And the result, G prime, is called a public key. And with this public key, Bob can encode its message into a code word and apply some random errors to it so that it becomes the cipher. Receiving the cipher, Alice, the one who holds the private keys S, P, and generated matrix, she will make a transformation to the S, P, basically inversion, and also transform the generating matrix into the decoding matrix. And with them, she's able to decode and recover the final message. As we know that all the crypto systems that rely on the concept named a trapdoor. And so the attacker, since the attacker only knows G prime, and since it doesn't know S, generating matrix, and P, it cannot perform the decryption steps as we can see down there. So we ask a question to ourselves that can we still improve it? So we're thinking of reducing the computation complexity because the current binary Gopal code used by Mackey-Lee's system involves lots of finite field operations, which are time consuming. We also want to see if we can make it more parallel and more hardware friendly. We also want to maintain the same security level without sacrificing or increasing the key size. And of course, if it's possible, we want to make it parameterizable. So one idea is that since the bottleneck is the binary GAPA code. What if we can replace it with a faster and secure code? So here comes our proposal that we want to use a new code to replace the current binary GAPA codes so that the new Mac-Elise system can be even more secure and can be even more efficient. So we dig into the literature that in 1970, it's amazing that what we can find when we really come back to the ancient stuff. And those ancient research really inspire us, and sometimes they're forgotten, but they're really amazing stuff buried in it. So the Latin squares are interesting squares that it's an n by n matrix that one item only appears once in each column or row. So in 1970, Xiao made an invention that the Latin squares can be converted to a code called orthogonal Latin square codes. But it's easy to encode, decode, and it's fast. And unlike the most single error correction or double error correction codes we've seen, there's no limit to its error correction capability. So the advantages of using this code to propose our new Mac-Elise system is that if we come back to our expectations, that since we have optimized our algorithms of decoding this ORSC code, and we'll make it even faster. So that now looking at this decryption algorithm, we know that we only deal with AND, XOR, and AND operations. And if we look at this decoding equation, we notice that each bit can be decoded in parallel, and it does not rely on other bits. And of course, with this simple operations and also a sparse matrix multiplication, it can be made very hardware friendly and can easy to implement and optimize. And it maintains the same security level, and later we'll show that we can even achieve a smaller key size. And since Latin squares are easier to make, this new system can be made parameterizable. And this is our hardware architecture with the key generation, decryption, and encryption submodules. And this is a coprocessor to carry out the Mac-Elise system. And of course, we made all the critical submodules and with all the optimization and the parameter, and also they also can be parameterizable. As we evaluate our design, that it's when we compare to the best work we've known, based on the binary GAPA codes, which is a classical Mac-Elise, and we are at least 3.5 times faster than it. This is important because we're talking about millions of cycles. And since none of the work have provided so the complete hardware cost, we only listed our hardware cost and latency table here. It also shows that for our design, it's very easy to parameterize it. And for the key size, as we can see that usually we peak on error correction. So the key size are related to the error correction capability. If we're able to correct 100 errors, and we notice that at this point, we are 50 times smaller than the binary GAPA code, which is classical Mac-Elise system. And of course, we need to do the security analysis with this design, and we apply the common attacks to code-based or Mac-Elise crypto systems, and our design is resistant to all of them. For the future work, of course, we want to do more security analysis and achieve more efficient decoding and decryption. And we also found something really interesting that we can use the binary or OSC code for non-binary code words, and which will result in an even smaller key size. And this is our new finding, and we plan to incorporate it in our next work. Thank you very much. Any questions?
Thank you, Lake. So if you have any questions.
President, may I ask a question instead of typing in?
Yes, please.
This is Maciek Ciesielski. Question, very interesting presentation. Thank you very much. On slide 18, you said that your reduced computation allows you to do the encryption with only AND, XOR, and add operations. Isn't that true for all systems, or is there the other system include multiplication or something like that? Why would that be drastically different from standard encryption systems? Or I mean, sorry, from McEllis system, which you're trying to improve by only allowing for AND or XOR and add?
This is a very good question. So, regular McEllis systems, and as well as some other post-quantum crypto systems, actually they all involve a couple of like finite field operations, such as vector multiplication and polynomial division and things like that. So of course, those are like those consist of they can consist of all and XOR. However, and this I would point out that so this proposed the new system, it only involves bitwise XOR, and so nothing like multiplication or division over the finite field. So this is much lighter. So that's why we call that lightweight system.
Very good. Thank you very much. Very convincing answer.
Thank you. Any other questions? How scalable is your design?
Oh, this is another good question. Actually, one of the biggest advantages of this design is that it's very scalable. So as we have said before, that one of our goals is that we want to make this parameterizable and scalable if it is possible. And as we dig into this code, like an orthogonal Latin square code, we found that it is very scalable. Like when you give it some parameters, and then it can quickly generate the corresponding encoding and decoding matrices. And when we substitute them into this McEllis crypto system, it makes the encryption and the decryption also very scalable. So if you look at the code and how it works, it will look like that if you give it parameters, and then it will automatically generate the corresponding encoding and decoding algorithms, and without actual effort. So this is one of the biggest advantages of this design.
Great answer. Thank you very much. Okay, so I would like to thank Lake again and move to the next presentation. Our fourth paper in session is going to be presented by Jin-Woo Kim. He is currently pursuing a PhD degree at Georgia Tech, and he will be talking about his paper on silicon versus organic interposer. So let's start the presentation.
Hello everyone, thanks for attending my session. I'm Jin-Woo Kim from Georgia Institute of Technology. Today, I'm going to present PPA and reliability trade-offs in heterogeneous 2.5D ICs using different interposer technologies. Interposer-based 2.5D integration provides the reuse of existing IPs, enables a heterogeneous integration, and significantly reduces design time and complexity by reutilizing chiplets as plug-and-play models. The recent Intel's Foveros and AMD Zen 2 architecture indicate that 2.5D technology is no longer an alternative to the traditional 2D SoC, but a new trend. In interposer-based 2.5D technology, silicon, organic material, and glass are commonly used for an interposer due to their characteristic. The silicon interposer has good performance and routing density, but the cost is higher than other interposers. In case of the organic interposer, it has low fabrication cost while it shows poor performance. The glass interposer has low cost and reasonable performance, but it is difficult to process and has poor thermal conductivity. Therefore, the overall performance, reliability, and design cost of 2.5D IC depend on the interposer technology. In this work, we design large-scale heterogeneous 2.5D ICs using silicon and LCP interposers. We also perform PPA analysis, signal integrity, power integrity, and manufacturing cost analysis on those designs. Finally, for the first time as far as we know, we observe quantitative trade-offs in terms of PPA, SI, PI, and fabrication cost depending on interposer technologies. The left figure shows our 2.5D IC design and analysis flow using commercial and in-house tools. From interposer and chiplet PDKs, chiplet-to-chiplet protocol, and netlist, our tool first generates interposer and chiplet designs. As the interposer wires are large, unlike on-chip wires, the I/O driver optimization step is taken before chiplet design stage for proper signal transmission. In I/O driver optimization, we generate multiple sizes of Intel's AIBs according to the wire length distribution of interposer. First, we implement the target interposer wire length as SPICE subcircuit by cascading TX line models from HFSS. Then, we perform the simulation over the wide search space of TX RX sizes and select the combination with the minimum propagation delay. Verilog netlist with selected TX RX sizes is generated and delivered for the chiplet design stage. Finally, we perform various analyses including PPA, SI, and PI for the design validation. In this work, we designed two 2.5D ICs based on silicon and LCP interposers. We choose silicon interposer technology based on TSMC CoWoS and LCP interposer based on Panasonic RF705S. When compared to silicon, LCP has one additional metal layer and larger physical dimensions in metal line pitch, micro bump pitch, and C4 bump pitch. In chiplet design, we choose a regular bump assignment, which is placing signal bumps in the center and power bumps at periphery to ease the IP reuse. Moreover, to minimize the wire length of chiplet-to-chiplet connections, we adapted area I/O placement to let I/O drivers be placed near their micro bumps. All chiplets are targeting the operating frequency of 1 GHz. Logic chiplets are designed with commercial 28nm technology, and IVR chiplet is designed with 130nm technology to take advantage of heterogeneity of 2.5D. In LCP design, the footprint of each chiplet has increased because of 3.75 times larger micro bump pitch than silicon design. In case of NOC and memory controller chiplets, the area of micro bump array dominates the logic area, so the chiplet areas have increased by 14.06 times. Because of the longer wire lengths in LCP chiplets, the switching power of each chiplet has increased up to 30.4%, which leads to the total power increase. For effective power delivery, top two metal layers are used for PDN in all chiplet designs with 20% of maximum occupancy. All chiplets satisfy the worst IL drop, less than 5% of supply voltage. In interposer design stage, we place all chiplets and passive components on the top side and all C4 bumps at the bottom side. For the passive components for IVR, we choose the solenoidal embedded inductor and low-profile capacitor. Before the signal routing, we place the mesh-type PDN on the lower two metal layers. Total 1,420 nets are routed through the interposer layers in all designs. An LCP interposer used one more metal layer than silicon interposer for the routing resource. As design rules in LCP's interposer are larger than silicon, LCP interposer has 4 times larger area and 1.8 times larger maximum wire length than silicon interposer. In this slide, I will present how we analyze 2.5D ICs. For timing and power analysis, we first generate transmission line models in the interposer design. We design the unit cell model with PDM mesh using HFSS and cascade them to generate full transmission line model. We run SPICE simulation with the following test bench for the analysis of transmission lines. Timing and power analysis results of chiplets are directly obtained from Synopsys prime time. For signal integrity, we first choose the complex channel model from our interposer design as shown in the figure. The channel model is then divided into 5 segments, and all are characterized to as parameter models. We import segment models into Keysight ADS and run simulation with the data rate of 1 Gbps and the crosstalk model at each input of aggressor. For power integrity, we perform frequency domain and time domain analysis. To model our mesh-type interposer PDN, we choose transmission matrix method to divide interposer PDN into n by n unit cells as shown in the figure. Each unicell is modeled as a lumped pi model with frequency-dependent RLGC elements. By cascading those unicell models, we analyze interposer PDN impedance and the transient characteristic of power delivery, including IVR chiplet. All analysis results will be discussed in the next slide. The table on the right side shows the overall comparison between silicon and LCP designs. As I mentioned in the previous slides, LCP interposer shows 4 times larger area and 1.76 times longer average wire lengths than silicon interposer because of its larger physical dimensions. Since LCP design has longer interposer wires, I/O power in LCP design is 1.33 times higher than silicon design, which mainly leads 1.1 times higher in total power. In signal integrity, LCP design shows 21.94% smaller eye height than silicon. This smaller eye height comes from intersymbol interference because of the impedance mismatch at the receiver side in LCP design. Because of 0.02 times smaller resistance in LCP transmission line, the reflected signal distorts other signals in the victim line. In terms of interposer PDN impedance, LCP design shows 0.95 times smaller DC impedance and 2.34 times better bandwidth approximately. For power integrity in time domain, LCP design has 1.62 times higher initial ringing and 1.33 times larger output ripple than silicon, whereas others remain similar. Higher ringing and ripple come from smaller inductance and capacitance in LCP design due to its lower dielectric constant and higher dielectric thickness. These overall comparisons between silicon and LCP designs show the trade-offs in terms of PPA, signal integrity, and power integrity depending on interposer technologies. In this slide, we perform the cost analysis on two 2.5D designs. The total cost of 2.5D design can be divided into interposer, chiplet, and bonding cost for simplicity. We estimate the overall manufacturing cost using parameters in the left table. From our estimation, the total cost of LCP design is 2.69 times higher than silicon design as shown in the right figure. Even though the interposer cost was 1.91 times less, the chiplet cost was 4.2 times higher because of larger area of chiplets in LCP design. We also performed the cost estimation of LCP design assuming interposer technology improvement same as silicon interposer. In predicted estimation, the interposer and chiplet costs have reduced to a quarter approximately. This predicted result indicates that the dimension improvement of LCP interposer is necessary to maximize its low-cost benefit. To summarize our work, we conducted quantitative comparison in terms of PPA, reliability, and cost between silicon and LCP interposer-based 2.5D ICs using commercial quality designs and simulations. We developed PD analysis framework which integrates frequency domain models into time domain simulations. Our work observed a wide range of trade-offs between two 2.5D designs in all aspects. Thank you.
Thank you, Jimwoo. So let's move to questions. Anybody has any questions? Okay, so I have a question. So why is the eye height of silicon design better than LCP design?
Hi, can you hear me?
Yes.
Yep. Yes. Okay. So in case of silicon design, so there's also the impedance mismatch at the receiver side. But in case of silicon design, the transmission line is lossy transmission line when compared to the LCP design. So that's the reason the reflected signal attenuates faster than LCP design. So that's the reason that interference effect is not showing in the silicon design eye height.
Okay, thank you. Any other questions? So you mentioned this interference effect, right? So don't we have interference effect in silicon design?
So there is, but the effect is really lower than LCP design because mostly when we see the impedance matching in silicon design, is a really almostly matched in silicon, but in case of LCP, the impedance of the transmission line is really fatter than the silicon interposer. So that's the reason that the big, huge impedance mismatch comes in the LCP design. That was the reason the difference between the silicon and LCP interposers.
Okay, excellent. Thank you very much again.
Thank you.
So I'll move to the next presentation. Next presenter is Henyu Zhao. Henyu is a fifth-year PhD candidate from UC San Diego. And he mentioned here that he's on job market now, and he's interested in full-time position opportunities in computer architecture and software. So if anyone from industry watching, I think he will be a good candidate. Now let's move to his presentation.
My name is Henyu Zhao. Today I will present our work, training scenario perception of layered computing system design in autonomous vehicles. This work is collaborated with Shuibo, Iran, and Tianchen from Hongyi AI, Hui, and my advisor, Professor Jishin Zhao from UC San Diego. Let's get started. This work is an academia and industry collaboration work. We run industrial level 4 AV feeds, various locations, load conditions, and traffic patterns. We also captured multiple near accident scenarios, and I'm going to show one of them. In this case, our AV refers to the autonomous vehicle, is crossing the intersection. Another white car is also crossing the intersection from the right side to the left. If our AV cannot perceive this white car immediately, if our AV cannot perform emergency braking operations in real time, collision will definitely happen. Okay? Based on this case study, we observe that AV safety is highly sensitive to the computing system. Let me briefly introduce the state-of-the-art level 4 AV system. It is composed by 3 major functions: localization, perception, and planning control. The entire AV system is run on a complex heterogeneous system. It includes high-end CPUs and high-end GPUs. In this work, we are focusing on the perception optimization because the perception is the most time-consuming module than the other two. In perception, we also observe that LiDAR perception consumes around 65% of the total computing system latency. And how does the AV computing system integrate the real world? And it widely used technology is called occupancy grid. This will help us to understand how the AV understands the real world. Let's imagine we are dividing the real world into multiple smaller grids. And then if we put an obstacle in the real world, some of the grids will be occupied by the obstacle. And in this figure, the red grids are occupied by obstacles. And each grid has a grid value and a grid coordinate. The grid value refers to the probability that an obstacle exists in that grid. Okay? To optimize the perception latency, we also want to understand which factor will contribute the most to the computation latency of the perception module. Okay? And we also made some observations that the latency of each perception module is determined by obstacles and computation resource allocations. And to understand the relationship between obstacle and perception latency, we build this perception latency model. In this model, we have 3 levels of the obstacle command. Each obstacle command is composed by multiple grids. And at level 1 optical command, the grid size is the smallest, so we have a lot of the grids. Okay, at level 2, the grids, we slightly increase the grid size. So for a given area, for a given region, we will have lesser grid count. Okay, and for the level 3 optical command, only one number, that is the total count of the obstacles. And then we will combine these 3 levels of the obstacle maps to generate the obstacle density distribution vector. We also generate a computation resource allocation vector, which refers to if we schedule a specific module to either GPU or CPU. And we forward these 2 inputs to the latency model, and finally we compute the latency of each software module. And with this model, we build a connection between the obstacle and the perception latency. Okay, and as we already have the latency model, how can we optimize the perception latency further? Okay, so that we propose the resource management scheme. Each resource management plan refers to that if we schedule the software modules to either GPU or CPU, or we need to determine the execution priority of each module. And to perform the resource management plan, we collected a lot of data samples. Each data sample includes the obstacle vector for the given obstacle distribution, and also the latency of each software modules. We apply different resource management plans to all of these samples, and we will select the best plan for each sample that will lead to the shortest latency for the given obstacle distribution. And we classify the samples into multiple clusters. If some of the samples are sharing the same plan, then we will classify them to the same cluster. And we'll calculate the obstacle vector for each cluster as a feature vector. And then when the AV is operating on road, just only needs to select the appropriate plan for the current obstacle distribution. We also made a little bit modification in the system. And then we modified slightly in the CPU part. First, we added the comparator to determine if there is a timeout. Timeout refers to that if the LiDAR latency is longer than 100 milliseconds, because the LiDAR working frequency is 10 Hertz. So if LiDAR perception latency is longer than 100 milliseconds, which means the computing system cannot process LiDAR data in real time. Next step, we added the counter to determine if the timeout is continuous or not. Continuous timeout refers to that if there are, for example, 100 timeouts happen continuously. And finally, we will match with the current obstacle vector with the feature vector for each clusters. And if there is a match, we will directly fetch, the AV will fetch the resource management plan from a memory and apply it to the AV system. Let's see some evaluation results. And this figure shows how we evaluate the latency model. We are showing the level 3 obstacle map to level 1 from top to bottom. The deeper color refers to that the obstacle in that region will contribute more to the perception latency. Okay. And based on this result, we conclude that nearby obstacles contribute more to the latency. And obstacle density also contributes more than the obstacle distribution. We also demonstrate the accuracy of this model. We achieve the average error rate of as low as 0.017%. We also evaluate our resource management plan when controlling and achieve a much lower energy consumption, and also we achieve We'll also optimize the average latency of LiDAR perception in the entire system significantly. Let me summarize this talk. In this work, we observe that the perception latency dominates the level 4 AV system response time. To optimize that, we also propose perception latency model to study the relationship between obstacles and perception latency. We also propose a resource management plan to optimize the perception latency. And we demonstrate that our design can achieve high accuracy, low latency, and low energy consumption.
Thank you. Thank you, Engin. So now we will move to questions. Do you have any questions? You can unmute yourself and ask your questions. Okay, let me ask a question here. So could we apply this latency model to other perception modules such as camera or radar?
Hello. Hi, can you hear me?
Yes, we can hear you, Anu.
Okay, thank you for the question. So basically, if we can use the same technology to model the obstacle distribution and obstacle density of other perception methodologies like camera or either a radar, LiDARs, we can definitely apply this latency model to the other sensor perception. Because if we model the obstacles in the same way we are using the occupancy grid in this work, and we just use we just use different sensors to represent the probability in each grid if some obstacles exist in that grid, so we can apply this to any other kind of perceptions.
Okay, thank you. Mm-hmm. Any other questions? If there are no questions, we don't have too much time, so I would like to move to the next presentation. Thank you, Henry, again.
Thank you.
Okay, so our next presenter is Anuradha Ranasinghe. I'm sure I'm not doing a good job pronouncing this, but hopefully close enough. So he is from University of Twente in Netherlands, and he will be presenting his work. So I'm going to move to the presentation.
Hello everyone, my name is Anuradha Ranasinghe, and I'm from EMCS class group of University of Twente, Netherlands. And today's my presentation is about a MEP-NTC, a standard cell library design scheme targeting for near threshold voltage computing. And this is my presentation outline. So I will give a brief insight to supply voltage scaling and near threshold computing. And then the concept of MEP-NTC will be discussed, and the key figures of merit of MEP-NTC style will be evaluated with other logic styles. And finally, the conclusion will be drawn at the end of this presentation. For most of the emerging battery-powered IoT technologies, energy efficiency has become the primary design goal. And the energy efficiency can be related to the power consumption of the device, and therefore running at minimal allowable VDD level, as well as minimizing the effective switching capacitance are promising ways to achieve the energy efficiency of these devices. In a system level point of view, this can be achieved in several abstraction levels, but in our case, we are only interested at circuit and logic level designs. So in a nutshell, we are exploring an alternative logic style to gain energy efficiency in digital hardware. The supply voltage scaling can be identified in 3 operating regions of transistors, and among them, the near threshold voltage region is the ideal region for energy efficiency because of its balanced trade-offs between the power consumption and delay. And with this, the scaling of the technology node, this the region that gives a minimum energy point slowly shifts towards higher voltages. That is due to the increased interconnect capacitances and increased leakage. By exploring an alternative logic style, we are trying to achieve a better energy curve and lower minimum energy point. So to target for better energy efficiency, we identified following important steps in the MEP-NTC design scheme. So we exploit parasitic behavior in MOSFETs for lower switching capacitance, specifically the gate parasitic capacitances of transistors. And we try to preserve the robustness of the circuit either with a transmission gate pair at the expense of a few extra transistors for the complementary signal generation, or inverse narrow width effect. So in the inverse narrow width effect, there's a possibility that the threshold voltage of the transistor can be modulated for a certain range of the width of the transistor. However, this also has a negative impact to the transistors. First, it increases the leakage, and on the other hand, it also increases the gate parasitic capacitance due to the stacking and due to the multiple devices of the transistors. However, under MEP-NTC scheme, we selectively apply the inverse narrow width effect only for the critical transistors in the circuit. And apart from that, we also consider some topological transformations to speed up the circuit. The steps in the previous slide can be graphically summarized as follows. From the logical mapping to the circuit is straightforward, and we are using Shannon expansion theorem for that. However, the initial circuit generated from this mapping is not energy optimal. If we further exploit the complementary nature of NMOS and PMOS devices, one of the extra inverters can be removed from this circuit. And apart from that, we then apply the inverse narrow width effect aware sizing for the critical devices in the critical path of this circuit. Another important step in the MEP-NTC style is reposition of the critical devices to the output node of the circuit. So for an example, for this OA21 cell, reposition of these PMOS devices to the output node reduces the critical path greatly. The third step is for the standard cells of multiple logic levels. So in this case, we have a full adder circuit, and we try to synchronize the internal signals as much as possible. And at the same time, if there's a possible glitch generated due to the synchronization issues, that will be cancelled out by the parasitic RC filtering at the second stage due to the capacity termination of these signals. Now we are looking at the key figures of merit of MEP-NTC cells. For this evaluation, I'm considering a subset of certain cells from several alternative libraries and standard CMOS library for this comparison. The main reason to pick the NXOR full adder and A021, OA21 type of cells is that this subset fairly reflects the features of MEP-NTC style compared to other logic styles. And as you can see, for AND, XOR, and full adder type of cells, the MEP-NTC scheme is nearly delivering up to 17% to 52% for different supply voltage levels. However, this trend doesn't follow for some of the complex compound gates of standard CMOS library, because the complex compound gates in standard CMOS style is they require the least number of transistors for this function, and because of this reason, the MEP NTC style is only energy efficient only in few cases. The design level key figures of merit of MEP NTC style is evaluated here for typical 0.5 volts near threshold voltage operation. And for this evaluation, we are considering 3 more library variants from standard CMOS library and INWE aware CMOS library, and a combined library from standard CMOS and INW aware CMOS size. And each library has nearly 30 to 40 cells with 1x and 2x drive strength operation cells. And all the cells have been characterized, including the CCS and CCSN noise modeling in cadence liberated software for typical near threshold operation at different corners. And we consider 4 benchmark circuits for energy efficiency evaluation. And each benchmark circuit is synthesized over these 4 different libraries, 4 different constraints. So the first figure we are looking at is for a 32-bit boot multiplier. And as you can see, the INW aware CMOS library is the most energy consuming library because of the INW aware sizing applied to all the cells. As mentioned earlier, it is not recommended for energy efficiency. And interestingly, the MEP NTC design style is the most energy efficient design, saving nearly 18% at most stringent constraints, and nearly 28% at most relaxed constraint against the CMOS and IMW CMOS combined library. Interestingly, the standard CMOS library fails to meet the constraints beyond 100 nanoseconds. In order to also verify the accuracy of the characterization, we also ran a SPICE simulation to the multiplier, and we observed that the SPICE accuracy to the CCS, the SPICE values, the SPICE energy values are nearly 5 to 77% accurate to the CCS characterization result of this multiplier. The other 3 benchmarks were a 25 tetra FIO filter, and a forward discrete cosine transform unit, and a JPEG encoder unit. So as you can see, the same observations can be made also for these 3 benchmark circuits, but saving nearly from 30% to 60% of energy saving at the expense of a slightly higher area for the MEP NTC scheme. So to conclude our work in this paper, we have presented a novel standard cell library design scheme for sub and near threshold voltage operation. And the proposed scheme provides rail-to-rail full swing operation, which is robust at ultra-low voltage levels. And we reported nearly 30 to 60% energy saving for general purpose hardware accelerators against at the expense of 12 to 15% area penalty. And at the same time, the MEP NTC cells provide balanced noise margin curves across a wider supply voltage range, and also for acceptable PVT variation resonance. And that's the end of this presentation. Thank you.
Okay, thank you very much. So, any questions about Anuradha's presentation? Thank you, Anuradha.
Yeah, I have a question, if I may. I indicated
Please,
in the
go
chat. Again, this is Maciek Ciesielski. Thank you very much. That's an interesting topic, and looks like a very interesting technique to save power. In your paper, you say you claim to have impressive savings of 30 to 60% in energy saving compared to CMOS, and this was I presume on the system level when you talk about 32-bit booth multipliers and the FIR filters. The question is how was this saving measured? Was it by simulation, in which case you would have to apply specific switching activity or assume specific switching activity, or was it measured actually on a physical hardware system?
Hi, thank you for your question. Do you guys hear me?
Yes.
Yes.
Yeah, okay. So for the all the benchmark circuits, the measurements were taken by running a specific switching activity on the hardware in the synthesized gate level netlist.
Okay.
Yeah, so for an example, for the booth multiplier, the simulation was performed against a uniformly distributed random test pattern, in which the consecutive test patterns do not have any correlation.
I see. Yeah. Okay, thank you.
Thank you.
Okay, thank you very much. So maybe one short question from me also. What could be the effect of interconnect capacitance of the proposed scheme?
Yeah, that was not included in the paper, but we recently ran an experiment on RISC-V processor on both libraries, using both libraries, standard CMOS and MIP-NTC style. So the interconnect energy contribution was measured to be around 15 to 20% for both libraries. So the reason for these comparable figures I see is because all the cells were designed in the layout to have the layout interconnects only to metal 1 routing, so that higher metal layers have enough room to access all the cells. Because of this reason, the metal density across both the designs were similar. So similar energy contribution.
Mm-hmm. Yeah. Okay, thank you. Thank you, Anuradha. So I'm going to move to our last presenter, Heming Zhen, who's a graduate student of Shanghai Jiaotong University. So he's going to talk about the cloud storage system. So let me move to the presentation.
Good morning, everyone. My name is Heming Zhen. Today I will present the study we have done in Shanghai Jiaotong University, FAGR, an efficient file-aware graph recovery scheme for erasure-coded cloud storage systems. Nowadays, flash memory is widely used in cloud storage systems. However, hardware failure and data loss are common in flash storage, especially in MLC and TLC flash. So high reliability is necessary. Replication is the traditional method to provide high reliability, but its storage cost is high. To ensure high availability and reliability of cloud storage systems, erasure coding is a typical method with low monetary cost. In the last 2 decades, several popular erasure codes are proposed. For example, RSKR can tolerate up to R failures, and data can be recovered from arbitrary K blocks. So RS32 erasure-coded system can provide better reliability than replication with lower storage cost. However, due to high failure risks of these drives, a challenge issue is how to shorten the recovery process. In the past 10 years, a few recovery methods are proposed to accelerate the recovery. Some methods speed up the reconstruction via pipelining in the device level, like partial parallel repair pipelining, and fast predictive repair. Meanwhile, several methods are given to reconstruct the hot data in advance, which investigate the data access patterns from upper-level applications. One of the state-of-the-art recovery methods is PBR. It splits the recovery process into independent tasks to enhance parallelism. The key idea of repair pipelining is to split the recovery process, but in a fine-grained manner, and pipeline the subtasks. For faster predictive repair, it models a bipartite matching problem for scheduling migration and reconstruction in parallel. This table is a summary on various fast recovery methods. From this table, we know that for faster recovery methods in the application level, they can speed up the hot data recovery, but achieve low performance because the recovery process is out of order based on the hot data distribution. Therefore, the pipelining methods in the device level cannot be applied. On the other hand, device level recovery approaches result in high recovery time on hot files because the file mapping and data access patterns are not recorded. Overall, existing methods cannot investigate the relationships among blocks, files, stripes, nodes, access frequencies, which reflects to a tremendous and complex graph. It motivates us to propose a novel method called FAGR to enhance the recovery performance in this paper. Now I'm going to introduce our file-aware graph recovery scheme. A recovery process of FAGR can be divided into 3 steps. First, the metadata information of files and blocks are collected, which is provided by the storage system. Second, a corresponding mathematical graph model is established based on the metadata information, and possible recovery paths can be evaluated based on the analysis on the graph model. Third, lost data is reconstructed according to the recovery path and optimized from the file point of view. Next, I introduce terms in FAGR. Run is a basic time unit of the recovery process, in which files can be recovered partially or entirely. An online node is one of all surviving nodes. A hot spare node is a node to store the recovered blocks. Then let's turn to the construction of FAGR graph. There are 6 types of vertices: files, stripes, blocks, nodes, and 2 special vertices, source and destination. Typically, a file in an RSKR-coded system is divided into several stripes, and each stripe consists of K+R blocks. To reflect relationships among different vertices, we use edges to delegate the mappings and distributions among these vertices. There are 2 properties of edges. The capacity is used to measure the maximum amount of data transmission required for a recovery task or subtask. The access frequencies reflect the hotness and the recovery priority of a file. To improve file level recovery performance, we have 2 goals. First, files with higher access frequencies are given higher priorities. Second, recovery tasks are evenly allocated to hot spare nodes and online nodes to avoid congestion. For simplicity, here we define a flow as a subgraph. Please refer to our paper for formal definitions of flow and maximum cost of flow problem. The value of each edge is less than or equal to the capacity. In this way, a flow can represent a recovery scheme due to the properties of FAGR graph. The cost of each edge is the weighted sum of value times frequency. Let's take an example here. The values of SOF0 and SOF1 are both 2. The values of other red edges are 1. The frequencies of SOF0 and SOF1 are 3 and 2. The frequencies of other edges are 0. So the total cost is 10. The cost of a flow reveals the cost efficiency by taking both the hotness of files and the amount of data transmission into consideration. Therefore, you can find a recovery scheme that achieves the 2 goals by finding the maximum cost flow in the FAGR graph. In the example figure, we can see that the maximum flow is marked with red, and the total cost is 10. Finally, After constructing the recovery scheme, FAGR can use any recovery methods like PBR and RP to manage the data transmission and support the EC computations. And the recovery process will be finished round by round. Let's illustrate the process of FAGR with a case study. The parameters of the case are listed on the left. In each round, FAGR find the maximum cost flow and finish the corresponding tasks. For example, in the first round, S0 is recovered through N0 and N1, and S2 is recovered through N2 and N3 because of their highest frequencies. Furthermore, FAGR avoids certain nodes such as N1 participating in the recovery process of more than 2 stripes concurrently. Round 2 and round 3 are similar to round 1. To demonstrate the effectiveness of FAGR, we set up a cluster of 30 Docker containers. Use 4 traces to obtain the basic information of files and implement FAGR with JErasure library for simplicity. The evaluation platform and trace information are shown in the table. We use several metrics and methods to evaluate our scheme. In static workload evaluation, we use recovery time on different file proportions as metrics. While in dynamic workload evaluation, we use response time and throughput as metrics. And the recovery methods for comparison are a typical recovery method, PBR and RP. Compared with typical recovery method, RP and PBR, when changing the number of hot spare nodes, FAGR can reduce the top 40% files recovery time by up to 58.06%, 57.37%, and 59.04% respectively. When altered the RS code parameter, the maximum reductions of recovery time are shown in the table. Besides, FAGR can reduce the average response time by 81.62%, 51.11%, and 68.16%. Improve the throughput by 4.44 times, 1.31 times, and 2.14 times when changing the RS code parameters, and the number of hot spare nodes in dynamic workload evaluation. In conclusion, FAGR can integrate the state-of-the-art fast recovery methods to improve file-level recovery performance in different recovery environments, and the evaluation results demonstrate its superiority over existing approaches. Thank you very much for your time.
Okay, thank you very much for the presentation, Emin. It should be really late in China now, so thank you for staying awake. So I have a question. There is nobody else is asking. If you have any questions, please unmute yourselves and ask. Okay, my question is, so the computational overhead of your method, so how much overhead is there?
Hello, can you hear me?
Yes.
Okay, thanks for the question. And actually, to reduce the overhead brought by our approach, we divide the recovery process into many rounds. And in many rounds, the number of vertices and edges are limited because we need to ensure load balancing. So the computational overhead of FAGR is reasonable. According to our evaluation, maximum time overhead is less than 0.5% under different RSKR configurations, which is negligible. In the meanwhile, the additional spatial overhead brought by FAGR is about 30 megabytes, which is also reasonable.
Okay, thank you very much. Any other questions? Okay, so if not, this concludes our first session, which was the best paper session. So we will have the best paper award for one of these papers at the closing of the conference, which is on Wednesday. Again, it will be selected by a special committee. Thank you very much for attending this session. Next, we will have our keynote, and our general chair will be presenting the keynote speaker.
Yes, thank you very much. I wanted to add one thing regarding the Best Paper Awards, that all the nominees for the Best Paper, those who presented those papers in this session, will be awarded, will be given a certificate of the Best Paper candidate. But the conference will come up with one Best Paper Award that will be given at this during the final session on Wednesday.
Yeah, so they will receive a certificate, Best Paper in Track, and Best Paper candidate. Thank you.
Right. Okay, do I have control now over?
Yes.